You know the distance from New York to Los Angeles? About 4,500 kilometers. A commercial flight covers it in roughly 5 hours. A rifle bullet? 75 minutes.
The SR-71 Blackbird, the fastest jet ever built, 32 minutes.
Voyager 1, launched in 1977, now beyond our solar system. New York to Los Angeles in 4 minutes and 20 seconds. Helios 2, the speed record holder before this decade, 1 minute, 4 seconds. And then, Parker Solar Probe, New York to Los Angeles, 23 seconds. The entire width of the United States in the time it takes to read one sentence out loud. 692,000 kilometers per hour, 195 kilometers every single second, the fastest object humanity has ever created. But here's the part that should genuinely disturb you. Even at that speed, it is not enough, not even remotely close. To understand why, we need to talk about distance, real distance, not the kind you see on a road trip map. I mean the kind of distance that breaks something in your brain if you sit with it long enough. Let us start small. The moon. You've seen it your whole life. It hangs there in the night sky, close enough to feel almost reachable. And in cosmic terms, it practically is. The moon is 384,000 kilometers away. Parker Solar Probe passes that distance in about 33 minutes. At full speed, it could fly to the moon and back before your lunch break ends. The sun is 150 million kilometers away. Parker covers that in roughly 9 days. 9 days to reach the star that has kept every living thing on this planet for 4.6 billion years. That is genuinely fast, faster than anything we've ever sent into space. And yet, the nearest star to our sun, a small red dwarf called Proxima Centauri, is 4.24 light-years away. Light itself, traveling at 300,000 kilometers per second, takes over 4 years to get there. And Parker Solar Probe, our fastest creation, it would take approximately 19,000 years. 19,000 years. Let that land. 19,000 years ago, our ancestors were painting cave walls in southern France. Agriculture had not been invented. The pyramids were 15,000 years in the future. Written language did not exist. And if we had launched Parker Solar Probe that very day by firelight inside that cave, it would be arriving at Proxima Centauri approximately right now. That's the scale we're dealing with. That's what space actually is. But let's go back to the probe itself, because the speed is only half the story. The Parker Solar Probe was launched on August 12, 2018. It's named after Eugene Parker, a physicist who in 1958 proposed the existence of the solar wind, a constant stream of charged particles flowing outward from the sun in all directions. The scientific community laughed at him. His paper was rejected. His idea was called impossible. He was right, completely undeniably right. And 50 years later, NASA named a spacecraft after him. Parker was 91 years old when he watched it launch. He stood there, an old man squinting at a rocket disappearing into the Florida sky, knowing that what he had imagined as a young scientist was now physically real and burning toward the sun. The mission? To fly directly into the sun's outer atmosphere, a region called the corona, and answer a question that has puzzled scientists for decades. Here's the question, and it is genuinely strange. The surface of the sun is about 5,500 degrees Celsius. Scorching, obviously. But the corona, the outer atmosphere that extends millions of kilometers into space, is over 1 million degrees Celsius. In some regions, closer to 3 million. Think about what that means. The atmosphere is hundreds of times hotter than the surface it sits above. If you stood next to a bonfire and the air 10 meters away from it was 1,000 times hotter than the fire itself, You wouldn't believe it. It would make no sense. It would violate everything you understand about heat. And yet, the sun does exactly this every day for 4.5 billion years. And we had no idea why. That's why Parker was built. That's the question it flew toward the sun to answer. Now here is where engineering becomes something close to art. If you are going to send a spacecraft into the atmosphere of a star, into temperatures exceeding 1,000,000 degrees, you need to solve a problem that has no precedent in human history. You need to protect a machine full of sensitive instruments from conditions that would vaporize most metals in seconds. The solution is called the thermal protection system. It is a heat shield 11.4 centimeters thick, made of carbon composite foam sandwiched between two carbon fiber panels coated in a white ceramic paint that reflects heat rather than absorbs it. The shield is about 2.4 meters across. It weighs 73 kilograms. On the sun-facing side of that shield, temperatures reach 1,370 degrees Celsius, hot enough to melt steel, hot enough to turn aluminum to liquid in moments. On the other side of that shield, 11 centimeters away, the spacecraft's instruments operate at roughly 30 degrees Celsius, room temperature, comfortable, almost boring. 11 centimeters, the width of your forearm. That is all that separates the probe from annihilation. And Parker does this not once, but 24 times, 24 orbits around the sun, each one bringing it closer than the last. At its final closest approach, it will come within 6.1 million kilometers of the sun's surface. Mercury, the innermost planet, orbits at an average of 57 million kilometers. Parker will fly 10 times closer than Mercury, inside the orbit of a planet, into the corona of a star, at 692,000 kilometers per hour. But let us return to the bigger question, because speed and engineering, as extraordinary as they are, only deepen the real mystery. We live in a civilization that can build a machine capable of surviving the atmosphere of a star. We can design a heat shield the thickness of a human arm that holds off temperatures that would vaporize steel. We can navigate a spacecraft with such precision that it can skim the surface of the sun and come back intact. And we still cannot reach the nearest star in any human time frame. Our solar system extends to a distant shell of icy objects called the Oort cloud, roughly 100,000 astronomical units away. One astronomical unit is 150 million kilometers. The Oort cloud is 100,000 times that far. At Parker speed, just reaching the outer edge of our own solar system would take 37 million years. Our solar system, our immediate cosmic backyard, is so enormous that the fastest object we have ever built could not cross it in the entire history of human civilization multiplied by 10,000. And the solar system is a microscopic speck inside the Milky Way galaxy. The Milky Way is 100,000 light-years across. At Parker speed, crossing it would take 450 billion years. The universe is only 13.8 billion years old. We would need more than 30 lifetimes of the universe itself to cross our own galaxy. And the Milky Way is one galaxy among an estimated 2 trillion. 2 trillion galaxies, each one containing hundreds of billions of stars. And the black voids between them, those stretches of absolute nothing you see in the Hubble Deep Field images, are millions of light-years of pure, cold, empty silence. So here is the question at the heart of all of it. If the universe is this vast, if even our fastest technology cannot begin to cross interstellar distance, then what does that mean for us? Are we alone? And if we are not, does it even matter? Because the distances between civilizations may be so incomprehensible that we never meet. We may send signals into the dark for 1,000 years and never hear anything back. Not because no one is listening, but because the universe itself is too wide for sound to cross in any meaningful time. The Voyager 1 probe, launched in 1977, traveling for nearly 50 years, is the most distant human-made object in existence. It is barely past the edge of our solar system. At that pace, it would take 73,000 years to reach Proxima Centauri, if anyone there could receive it. We sent a message into the dark, and the dark is bigger than anything we were built to comprehend. Parker's solar probe is different. It is not going outward into that darkness, it is going inward. It is not trying to reach another star, it is trying to understand our own. And in doing so, it is uncovering things about plasma physics and magnetic fields and coronal heating that could one day revolutionize how we generate energy on Earth, and possibly, one distant day, how we propel ships between the stars. That's a long game, the longest game our species has ever played, but it begins here, with a machine the size of a small car wrapped in 11 centimeters of carbon foam flying at 692,000 kilometers per hour into the fire. And here is the thought I want to leave you with. Parker's solar probe is the fastest thing our species has ever built. It represents decades of engineering, billions of dollars, and thousands of human beings who gave years of their lives to make it work. And by the standards of the universe, it is barely moving. That could make you feel small, and honestly, it should, a little. But here's the other side of that. We built it anyway, knowing it could never cross the galaxy, knowing the stars are impossibly far, knowing we are specks on a pale blue dot in the outer arm of one unremarkable galaxy among 2 trillion. We looked at all of that, at the full, staggering weight of cosmic scale, and then we got up and built a machine, wrapped it in carbon foam, pointed it at the nearest star, and said, "Let's go find out." That is what we are. That is what we have always been. And nothing in this universe, no matter how vast, has ever been able to make us stop.